Alright, thank you so much for taking the time to watch this video this evening and getting yourself ready for your chemistry test. As we do, I wanted to give you an opportunity to work through some problems and get as ready as possible. So what we're going to do is we're going to work through some of the example problems in the text here. We're going to start on page 79, getting you ready. So here's example 6.1 on page 79, and you'll notice it says in a certain process there are 45 joules of heat that was added to a system while the system did 155 joules of work on its surrounding. What was the delta E for the system? So we know that the delta E value, we're going to have a formula. Our formula, first of all, delta E, let me try to do this with this pen. Delta E is equal to Q plus W. And so that's what we have. Q stands for energy in the form of heat, and W stands for energy in the form of work. And so we're going to write these over here. Q is equal to, and we're going to find the value is 45 joules of energy. And because heat was added to the system, it is going to gain energy, so the sign of this will be positive. Okay, and then because the system did work on the surrounding, it's going to lose energy. So we're going to get W to equal negative 155 joules. And so that's what we'll have. We're going to take our value then, we're going to take delta E is equal to, and we're going to plug things in. We're going to take our 45, and we're going to add to 45 negative 155 joules. Okay, at the very end of this problem, we will get our internal energy of the system to equal the combined value of both of these. If I can get myself to page 79 as well, I will tell you the answer to that. You've got your calculator with you. You can answer the question briefly there. Probably already have. Negative 110 joules. Okay, negative 110, of course, these are accounting for significant figures. So 110 point, so 3 sig figs joules. And so there is our final answer there. Let me clean that up for you. So there's our final answer for example 6.1. From there, we move on to, I'll give you a second to look at that, pause the video if you can. And then from there, we're going to look at example 6.2. Example 6.2 is a different type of question. It deals with specific heat. Specific heat comes into a very specific type of formula. Page 82, you will see that one. It says how much heat is lost by a piece of copper with a mass of 50 grams when it cools from 95 degrees Celsius to 20 degrees Celsius. Then it says, hey, the specific heat of this is 0.38 joules per gram degree Celsius. So what we're going to do is write out our formula. The formula for this is Q is equal to MC delta T. And so I'm looking for the amount of heat, how much heat is lost. That's going to be my Q value here. Okay, so I'm looking for that before the end of this problem. So piece of copper with a mass of 50 grams. So at this point, we can write down what we have. We have this is our mass is 50 grams. We have this is the from this, so it's temperature initial here, and it will end at temperature final at 20 degrees. And so that's what we have so far. And then we have our C value right here, the specific heat for copper, CCU. And so here we're going to plug into our formula. Q is equal to M, and that's simply going to be 50.0 grams. Okay, and then we're going to take our value for this, that is 0.38 for copper. Okay, and that's going to be joules per gram degrees Celsius. Okay, and then from there we're going to take 20, the final, 0.0, minus the initial, 95.0. And so this right here will give us our delta T value. So this is C, this is M, and that's delta T. And so from there, you want to obviously get your proper answers. And so setting everything up here, getting out my calculator so I can do some calculations as well. We're going to do 20 minus the 95. That's going to give me negative 75. So there's that, negative 75.0. Okay, that's degrees, by the way, Celsius. Here this is 0.38. And this is 50.0 grams. And so the units inconsequential at this point. Q is equal to grams here cancel. The degree Celsius cancels with the final term here. There would have been a degree Celsius here. And those will cancel, and our final answer will be left in terms of joules. So we're going to take 50 times 0.38, and then we're going to multiply that by negative 75. That will leave me with negative 1,425. Final unit is joules. And so there is our final answer in terms of energy for this question. So how much heat is lost? Now after that, you need to answer the question, why is it negative? Well, because the system is losing energy in the form of heat, we are going to say it is negative. From there as well, by the way, sig figs will approximate this to negative 1,400 joules for 2 sig figs to be final. So there is our final answer there, negative 1,400 joules. Okay, so that's the second example. This next one is a lot more involved, and so I'd like to spend a little bit more time on it. In the experiment to find the specific heat of lead, 49.8 grams of lead at 100 degrees Celsius was placed in a coffee cup calorimeter containing 75 grams of H2O at 21.0 degrees Celsius. The final temperature of the mixture was 22.7 degrees Celsius. The final question is, what is the specific heat of lead? Assume no heat is lost in the calorimeter or the surroundings. So here's what we're going to do. We need to set up this question by drawing a picture. I think I can zoom this out a bit. And over here I'd like to draw the first concept. So we have a cup here. This marker that I'm using is not the one I normally use, and so it's a little, my art skills on this aren't as good. So in an experiment we have our lump of whatever it would be. Gold was the one we did in class, but this one will be lead, so we'll use the symbol PB. And then we have water, H2O, here that we are putting this into, H2O. So there's that. Okay, so from there we have a setup. According to the law of thermodynamics, the first one, we can say that Q gained is equal to negative Q lost. All right, so now we need to mentally think through when we put the lead into the water, what's gaining heat and what is losing heat, because both will be true, both will be happening. So in an experiment to find the specific heat of lead, 49.8 grams of lead. So I know that I'm going to have over here my lead side of my equation. Over here I'm going to have H2O. I haven't said which one's gained or lost, but I'm going to consider lead and water separately. So lead, the mass of lead, is going to equal 49.8 grams. And over here we're going to get 75 grams of water, 75.0 grams of water. And that's going to be the mass of this water. Okay, so there's that. On the left, or on the right, we also know the specific heat of water memorized from a chart, 4.18 joules per gram degrees Celsius. And so there's that as well. This is the C4H2O. Okay, so now at this point we need to know the initial temperature of lead, temperature 1, or initial. We will know to be, it says it was at 100 degrees Celsius, so we're going to do 100 when it was first placed into the water, 100 degrees Celsius. And then when it was done, this is where it takes some time to think through. It says it was placed in a coffee cup calorimeter containing this, and at the end of the problem, the mixture was 22.7 degrees Celsius. So what we know then is that the final temperature, because no heat is being changed, let me change this final to a 2 so I can be consistent. So this will be a 2. So temperature 2 is going to be 22.7 degrees Celsius. Okay, both of these, excuse me hitting the mic there, both of these T2 will be 22.7, but the initial temperature, or temperature 1 for water, was found in the problem at 21 degrees. So it only went up just a bit there in Celsius. Okay, so now we've written everything. We're looking for the C of lead. And so I set up a equation. Give you a second to think about what's heating and what is losing temperature. So what we can establish here is that the side that is losing temperature, that is going to be the one that gets colder by the end of this. That is going to be our lead side. Let's see if I can get my eraser to work here. There we go. And so this is going to be my water side. It's going to gain the heat, and this side's going to be my lead side. So this is going to be my PB side. Okay, so exactly opposite of how I tabulated. So then we know that MCAT is what Q turns into, or MC delta T, and negative MCAT for the other one. Okay, so we know that the Q up here is going to equal MCAT, and the Q up here will be negative MCAT because it's losing energy. So plug in everything you know. So for water, we know this to be 75.0 grams. We know the specific heat of water is 4.18 joules. We know the delta T. The delta T is going to be calculated by 2 minus 1. The temperature 2 minus temperature 1, so 22.7 minus 21.0. And so this particular problem should be easy enough to do. And so we'll do 22.7 minus 21, and that'll give you a final answer of 1.7. Easy enough to do in your head, but I can't afford to mess this up in video. So here we go. So 1.7 is equal to negative. Over here we'll do the mass of lead, so that's going to be 49.8. Need to make my decimal clear up here, 0.8. And so there's 0.8 here. There is a C value, that's what we're looking for, CPB. And then we need to find the delta T. So the delta T is going to be found here. Let me move my screen. Okay, so information's there. You can see it in your text as well, but MC, and then I want to come over here and do this problem. So we have the 2 value, 22.7, minus 100. So we do the second temperature minus the first temperature. So now we have a bunch of numbers. On the left, if I multiply out this whole left side, what I'll end up getting is 75 times 4.18. Messed up my inputs. So 75.0 times 4.18. That gives me 313.5 times 1.7. That'll give me 532 on the left, so 532.95. And that is equal to negative. And then I'm going to multiply, first of all, I'll subtract this 22.7 minus 100 gives me negative 77.3. I'll multiply these two numbers, and so that'll give me negative 77.3 times 49.8. Now you'll notice that'll give me a negative, and that'll give me 3,849.54 on the right, and then I have the variable here of PB, so the specific heat of lead. Negative is a positive, and so I can ignore the signs. Now at this point, the simplest thing to do is divide by the 3,849.54. Okay, so this gets canceled, this gets canceled. Do that on this side as well, 3,849.54. And then I'm left with on the right side the C of PB, the specific heat of lead, and I'll put this into my calculator. So I'll get 532.95. I'll divide by 3,849.54, and that'll give me a final answer of 0.138. And then the units for specific heat are joules per gram degrees Celsius. So there is my final answer. Forgive me for going through the equal sign, but there is my answer. You can see the answer to this on page 83. These are also seen. So there's our answer. So there we have it. We're going to go on to a couple more here. 6.4, this is an enthalpy of formation equation. You'll need the chart on the top of 84, but you'll need to do the problem elsewhere. So calculate the enthalpy change from the combustion of ethanol used to power the V2 and Redstone rockets. So there is a reaction that's seen there. It's ethanol plus oxygen yields carbon dioxide and water. Okay. Then it asks us to tell if it's exothermic or if it's endothermic. That question can be answered based on the sign. So let's get our eraser here. Okay. Boom. Nope, doesn't want to erase it. Maybe it'll just do that magically. There it is. All right, calculate the enthalpy change of this. So basically, standard enthalpy is delta H standard, that's what it stands for, delta H standard, is equal to, and what we're going to do from here is we're going to say the delta H of the second, similar to what we did before, so the delta H of the products, the right side of the equation, minus the delta H of the standard of the reactants. Okay, and so that's what we have. We have the delta H, the enthalpy, standard enthalpy of this problem is going to be the standard enthalpy of the products minus the standard enthalpy of the reactants. So what we're going to do is we're going to go through and we're going to set up delta H is equal to, standard enthalpy is equal to, and we're going to consider just the products. Okay. Now if we look on the chart, we're going to see that carbon dioxide, CO2, in the gaseous form has an enthalpy of formation value. CO2 gaseous is, and I'm looking at it here, negative 393.5, and the units are very important, so kilojoules per mole. Okay, that is my value for CO2. And then H2O in the liquid form, because of course water can be other states of matter as well, H2O is going to be found near the bottom middle there, and it's liquid, so it's going to be negative 285.8 kilojoules per mole. Okay, so that gives me a value there. So what I'm going to do from here is I'm going to set up a set of brackets, and notice it's the kilojoules per mole. The number of moles comes from this, so I have 2 moles of this and 3 moles of water. So I'm going to set up a bracket, and I'm going to write the sum of them. So I have 2 moles of CO2. The value for CO2 is, the enthalpy for CO2 is 393.5 kilojoules per mole. Forgive the penmanship, working on getting skilled at this. And then plus, I need 3 moles of water, 3 moles, and then I'm going to plug this in, negative 285.8. Okay, 0.8, and then I'm going to close that. So that's kilojoules per mole as well. Well, you'll notice that the moles end up canceling, and this would also cancel with the kilojoules per mole. I'll try to scribble this in here. Okay, and so the moles end up canceling, and we're left with 2 values. All right, so calculator time. I'm going to take my calculator and I'm going to multiply 2 times negative 393.5. That's going to give me negative 787. So I'm going to just go ahead and simplify this bracket. Negative 787, and that's going to be in terms of kilojoules. Okay, that's my first quantity. Okay, from there I'm going to take my 3 and I'm going to multiply it by my other value. So I'm going to take 3 times negative 285.8, and that's going to give me another quantity of negative 857.4. Okay, simplifying the first bracket, we're going to do this just for our reactants. Sorry, excuse me, the products. We're going to take the 2 and add them together. 787 point, no, that's just 787. Okay, 787, and we're going to add to that 857.4. Keep the sign and add, and we're going to get, for our reactants, we're going to get 1,644. Excuse me, putting commas in weird places. 44.4. Okay, so that's our enthalpy for the reactant. Sorry, excuse me, the products, and that's in kilojoules. Then we go to the reactants. So I'll do my reaction or reactants here, and we have in our reactants up here at the very top of the screen, we have oxygen and we have ethanol, liquid ethanol. So liquid ethanol is C2H5. Let's see if I can find it on the chart. It's at the very bottom left, kind of third from the bottom. It looks to be, there's 1 mole of it, and that's going to be negative 277.7. Okay, kilojoules per mole. And that's plus. And then oxygen, because it is uncombined, is 0 kilojoules per mole, even though there's 3 of them. That just goes away. So then I'm left with, on the bottom, the reactants alone have negative 277.7 0.7 kilojoules. The moles cancel here. All right, so I have my reactants enthalpy of formation, and I have my products. According to the formula up here, I think I have a highlighter on my cursor. Up here, my reactants, I'm sorry, the products minus the reactor that I was supposed to put a negative here. Some of you were screaming that at me. This is a negative and a negative. That gives me a negative 1644, and I have also a negative 277.7 kilojoules. And so whenever I subtract them, my problem looks like this: negative 1644.4 minus negative 277.7. Okay, when I do this, I change the sign of the subtrahend and add. This will give me a final answer of negative 1366.7 kilojoules, and that is the answer in terms of enthalpy of formation. Now, the question at the top, whether or not it's exothermic or endothermic, it is exothermic. Forgive my circling here. It is exothermic, and the reason it's exothermic is that the sign of delta H is negative. So if the delta H of formation is negative, it releases heat. Okay, so there's that. Now, going down to one of the last questions, and this one's a bit longer, is the notorious heat exchange. This is page 87, and we'll notice how much heat is necessary to convert 25 grams of ice at negative 15 degrees Celsius to steam. Well, again, we've done this in the past, but we need to understand that we're going from a position here, we're starting at ice, and we're ending all the way up here at steam. So remember, at any of the slopes, we use Q equals MCAT. At any of the plateaus, we use Q equals M delta H of whatever fusion or vaporization. So that's what we need to know. So how much heat is necessary? Well, we start down here, and I think I'm highlighting this. I assume it's true. So here at this value, for instance, we start at 25 grams of ice at negative 15 degrees. So we go ahead, and for our slope, we're going to say Q is equal to MCAT, MC delta T. And in order to do this for ice, the question is, how long is it ice? Well, Q is equal to, and we have the mass. The mass doesn't change through the whole problem. So that's 25.0 grams. Then we have the specific heat of ice. Now we have to go back to the page that had that value, flipping here for you. The page that has the specific heat of ice is page 81. It says the specific heat of water, or ice, I'm sorry, is 2.06. So here it is, 2.06. And then our delta T. It starts, so remember the final minus initial, temperature final minus temperature initial. If it's ice, it's initially at negative 15.0 degrees, and we're going to subtract that from where it ceases to be ice, so 0.0 degrees. Okay? So then that means we're going to change the sign of the subtrahend and add. So we're going to have Q is equal to 25.0 times 2.06. In our calculator, we're going to get 25.0 times 2.06. Gives me 51.06. We do 15 times that. And we're going to take the energy just to change or get to the plateau is going to be 772.5 joules. Okay? And that's going to be my heat needed. So that's the energy just to rise up this piece. Then we have to go here. Okay? So that's the Q of ice. I'm going to go ahead and box that or circle that so I know to use it. We're going to add them all up at the end. And now we still have ice. We need to basically melt this. We're going to use the concept of fusion. And I believe there's a chart at the top of 87 that has the delta H of fusion for me. Delta H of fusion for ice, in this case they're calling it water, is 334 joules per whatever. So now for the plateau, we're going to use this Q for the phase change is going to be M delta H of fusion. Okay, F's fusion. So Q is equal to M, notice 25 grams, and I'm going to multiply that by the delta H. In this case, it's 334 joules. And this comes from a chart. So Q is equal to, for the phase change, 334 times 25. 334 times 25 is going to give me 8,350, and the term is joules, or the unit of energy is joules. So that's, so far, in order to go from this portion of ice, we have gained 772, that's over here, 772.5 joules. In order to go to melt the ice, we had to use 8,350. Now we have to go through this entire section of water. So over here, we'll start the Q for water. So then that's equal to MCAT as well. And then, so Q for water, the mass hasn't changed, so we still have 25 grams. Then we have the specific heat of water, same place, 4.18 joules. And then the temperature change. So it becomes water at 0. Remember, it's final minus initial. Okay? And so it initially is 0 because it would just became water. And at the end, it'll be 100 because that's our change. So it'll boil at that point. So we're going to do, we'll just call this whole value here 100. So then we simply take 100 times 4.18, which would give me 418 times 25, and we'll get this value. The Q for water is equal to 10,450 joules, and you'll notice that is an enormous number relatively to the other ones. Again, we have added so much energy, so it takes a lot of energy to melt it, to make it turn into the phase change, to melt it, then going all the way up the water slope. Now we have to go up here. We'll use the Q equals M delta H for vaporization now. And obviously that value will be much greater. So here we're going to do Q is equal to M delta H vaporization, same thing from the chart on page 87. Okay. Looking at it here. So I've got Q is equal to M, the mass is still 25, hasn't changed. And then the delta H of vaporization here for water is 2260. Okay, so then at this point I'm going to take my calculator and multiply 25 times 2260. And I'm going to get 56,500, so 56,500 joules. And so far I have all of the energy that's been used. So that's the energy so far. I've got the 772.5 to turn it to the phase change. I use about 8,000 of it to go between ice to water, or water to ice, vice versa. Okay. Then I use about 10,000 to make it water going into steam to get to the boiling point, 56,000 to get to here, and now we're going to steam. Now we just have a small portion left, again using Q equals MCAT. From there, we're going to say Q is equal to, the mass is still 25 grams. The C for this, going to need a C value for steam. Going back here a bit to find my specific heat value. For steam is 2.08. 2.08. So checking that and making sure I have it, 2.08. And then the delta T. Well, it's, again, temperature final minus temperature initial. Okay, and so it will end at 110 degrees according to the problem. And we're going to subtract that from what it was. It started to be steam at 100. Okay, so our delta T is 10. So we're going to take 20.8, nope, 2.08 times 10. 20.8 is what we have, times 25, and we're going to get 520 joules. Now the reason that's such a small number is because we haven't gone very far on the graph. We're still steam. Now, at the end, we want to know how much heat was needed to do the whole thing. We need to add all of these numbers up. So I take 772.5, I add 8,350 to it, I add 10,450, I add 56,500, and then I add 520. That gives me a final answer. Here's the Q total for the whole problem down at the bottom here. And that's going to give me 76,592.5. And this is all going to be in joules. And for the sake of time, I will go ahead and leave that as that. You can think about sig figs and all that. You can also consider kilojoules and all that. So that's my final answer for that particular question. 76,600 would be the 3 sig figs for that. And that leaves us with one last question, and that is an entropy problem. Okay, and that gives me this particular one. I'm going to hit the space bar here to give me some space to work. Okay, and then we will do this problem together. So the rusting of iron occurs according to the reaction. So we are looking at the Gibbs free energy equation. This will be seen on the page before it. Delta G, I'll write it up on the screen. Delta G is equal to delta H minus T delta S. Okay, remember delta G is Gibbs free energy. By the way, all of these are standard, and that's important for this. And then delta H is enthalpy, delta S is entropy. So what they've done is they've actually given us those values. Notice the units. The units are not acceptable here. It says calculate the free energy change under standard conditions. So what we're going to do is we're going to say delta G, Gibbs free energy, is equal to the enthalpy. Well, I have that over here, negative 1644. Okay, negative 1644. And that's in kilojoules. And then I'm going to subtract from that the temperature. Since it's standard, the temperature will be 298 kelvins. Okay, that's a known fact. Got to know that for the test. And then the delta S value is going to be negative 544 joules per Kelvin. Okay. Now, because both of these, one's in joules and one is in kilojoules, I'm going to replace kilojoules by adding 3 zeros to the end. Okay, a kilo means multiply by 1,000. So this gives me negative 1.6 million joules. Now I'll put the little joules there. Now, delta G then is equal to, and I'm going to go ahead and get my negative 16, or 1.6 mil here. And then I'm going to get this. Now, minus a minus will be a plus, so I'm going to go ahead and change that now, and I'm going to take 544 times 298, and that's going to give me 162. Okay, and that's going to give me those values. So from there, I'm simply going to combine those two numbers, and I'm going to get a final answer. My delta G value, Gibbs free energy, is equal to negative 1.4 million or so. And because it's energy, it's in joules. Kelvins cancel here, and we're left with joules. And so now the question is, what is the free energy change? Well, the delta value is going to be negative 1482 kilojoules. What I have is fine. I'm not in terms of kilojoules. You can do that if you'd like. Then the question is it spontaneous? Well, if this value is negative, we can conclude it is spontaneous. All right, so I just sat down to make this for you. I hope that it was helpful. I did scribble through this. I didn't necessarily teach it as much as I explained it and just walked through it. But my goal and intention from this is that it would be helpful for you as you get ready for your exam. I am hoping that it goes well for you. I'm thankful you watched this and you put the effort in to learn this. Keep working hard, and I'll see you in class.